What nerdy kid didn't want their own spectrometer? How cool would that have been? Halloween would have been completely different. The mystery of what exactly that candy corn is really made out of would have been finally solved. And those fake lips or teeth? I mean, they say it's wax, but is it really? I'm guessing some paraffin, maybe a red dye number 5. Unfortunately, most kid science lab budgets didn't include tens of thousands of dollars for an entry-level spectrometer. But times have changed, my friends. Hi, I'm Amelia Dalton, host of Chalk Talk, and today my guest is Trevor Dowd from TI. Get ready, because today we're going to talk about a new low-cost, high-performance spectrometer that uses TI DLP technology and fits in the palm of your hand. Before we get started, don't forget to click that link. There you can find out more information about TI's DLP technology. Hi, Trevor. Thank you so much for joining me today.
Yeah, thanks, Amelia.
Okay, so a lot of us know about DLP technology in terms of video projection for movie theaters or boardrooms, but I'm not exactly sure how this technology works.
Okay, so DLP technology works with what's called a DMD, or a digital micromirror device.
Okay.
On the surface, it looks like one big flat mirror, but when you zoom in, you can see an array of micromirrors, a couple microns on each side. And those micromirrors tilt one direction or another. It's a bistable solution.
Okay.
So when you have light projected onto the micromirrors, they can point the light towards a projection lens or to a light absorber to create pixels.
Okay.
So you can stitch all of those pixels together, hundreds of thousands or millions of micromirrors, to create an image. That's how cinemas work. That's how boardroom projectors and classroom projectors work.
Okay, cool. So let's talk about some applications. DLP technology is being used in a lot of cool stuff, right?
Yeah. Our technology is used in many applications outside of digital projection. So we're used in 3D machine vision, 3D printing, lithography, and also spectroscopy.
Okay, cool. Let's talk about spectroscopy.
Spectroscopy is a powerful technique for recognizing and characterizing physical attributes of materials by looking at the absorption or the emission of light that you shine onto them. So different materials have a different thumbprint of reflected and absorbed light that allows you to identify them. So if you split that light out into a rainbow of wavelengths, you can look at those light intensities to determine what you're looking at. And it's used in applications like food and agriculture, plastic identification, pharmaceuticals, petrochemicals, law enforcement, and medical applications.
Okay, cool. So, Trevor, what does the scan actually look like? Can we dive into some of those first examples?
Sure. So here's a scan of standard sugar or sucrose. Across the x-axis, you'll see the wavelengths from 1100 to 1700 nanometers. And the y-axis shows absorption. An important thing to point out is a peak just above 1400 nanometers that identifies sugar.
Okay.
And you can see that in the standard sugar graph and then also in the powdered sugar graph on the right.
Okay, Trevor, so why do I want to know about sugar content? I mean, I try to avoid knowing about that kind of stuff.
Yeah, so if you scan fruit, for example, you can determine if a piece of fruit is ripe or if it's gone bad by looking at the sugar content.
Oh, okay.
So here's a graph of several apples, and you'll see that same peak just above 1400 nanometers represented in all of those apples at different heights, showing how sweet the apple is. When it becomes too sweet, then it starts going bad.
Huh, all right. So I'm guessing that spectroscopy goes beyond sugar content in fruit, right?
Exactly, yes. So here's a graph of lotion analysis, for example.
Okay.
We graphed several different brands and kinds of lotion, from baby oil to conditioner, and you'll see a lot of the same waveforms represented in each of them.
Yeah.
Some of them have different characteristics that allows you to point out which one is which. So you can look at many different graphs of different kinds of lotions to determine which one you're looking at.
Okay. All right, so we're all engineers here, Trevor. Let's dive into some of the details about how we do this spectroscopy thing.
Sure, so first we'll take a look at the current dispersive architecture using a linear array detector. Up top, you'll see the sample with 2 lights shining on it. And those lights reflect off the sample, and that light feeds through some optics and a slit and some more optics, and then it hits a diffraction grating. And that diffraction grating spreads the light out across different wavelengths. Then those wavelengths individually go through some optics and run into a detector called an in-gas array detector.
Okay.
So there are many different detectors that make up that array, and it's a limited number of pixels, somewhere around 128 up to 1024. And they're very small in size because you have to fit many in the detector. And these array detectors are very costly. Now we'll turn towards how DLP fits into that equation. You'll see the top of the system is exactly the same. You have a sample and a slit and optics. You hit a diffraction grating and go through some more optics. But now instead of an expensive linear array detector, we have the DMD. And the DMD is able to steer light one wavelength at a time towards a very large, very accurate in-gas point detector.
Okay.
So you're able to utilize the high resolution of the DLP array and a large detector to capture lots of light to get down the noise that you would see in the in-gas array detector. And DLP's programmability offers several advantages, like you can change the intensity of the light that you're looking at. You can change the integration time. You can have variable resolution. You can start to use complex Hadamard patterns. You can use custom spectral filters, and you can also compensate for optical distortion and physical misalignment.
Okay, cool. So I want to do some spectroscopy. How do I get started?
We have an evaluation module called the DLP NIRscan Nano, which is based on the DLP 2010 NIR chipset.
Okay.
It's a complete evaluation module to design mobile NIR spectrometers. It has Bluetooth low energy capability, and the evaluation module has a wavelength range from 900 to 1700 nanometers, and it's completely programmable. It has good signal-to-noise ratio, good optical resolution, and a very small form factor. It can fit in the palm of your hand.
Cool. All right, so let's look under the hood of this bad boy, Trevor.
So if you chop off the top of the evaluation module and look at the optics, this is what you would see. In the front is a window and 2 lamps. The lamps shine light in the form of the yellow arrows here out onto the sample, and that light is reflected back through that orange arrow, back through some optics and through a slit and some more optics, and then it hits a diffraction grating in the back. That diffraction grating splits up the wavelengths, which then go through some more optics and hit the DMD at the front part of the device. The DMD is able to turn on mirrors to shine specific wavelengths at the in-gas point detector. And it switches through those wavelengths in order to capture the absorption or the light emission of each of those individual points. So the EVM is an integrated electrical, optical, and mechanical design in a small form factor. And the mechanical features of the chassis are designed to enable high volume production with molded parts.
Cool. So it seems like DLP technology is pretty flexible. How does this help me make a better spectrometer?
Yeah, so in addition to the cost advantages, DLP offers complete programmability. There's adaptive control of critical scan parameters at each waveband, so you can change the intensity of each wavelength, the integration time, the resolution, and you can start and stop at specific wavelengths if you're just interested in looking at a certain area.
Cool.
So on the fruit that we measured earlier, if you just want to look between 1400 and 1500 nanometers to find that spike, you can do that.
Cool, okay.
We also have improved measurement sensitivity with Hadamard patterns. So you can turn on special Hadamard patterns which allow multiple wavelengths of light to go through at one specific time. That way, you're capturing a lot of light and lowering the noise level, and then you can use some math to determine which of those wavelengths had which intensity.
Okay.
Overall, you can get 7 times the amount of light into the detector based on column scans. You're also able to do real-time monitoring, so complex spectral filters based on the substance can be implemented to determine specific attributes. So if you're trying to compare good engine oil to bad engine oil, you can do that using a complex spectral filter.
Okay, so when I get ready to program this thing, how do I connect it up?
Our evaluation module is very flexible. You can connect to a laptop through a USB cable. On the laptop, you can use our PC GUI, which has source code available that you can change. And you can control the device, including initiating scans, setting different parameters, and downloading the data. You can also connect through Bluetooth to your PC, tablet, or phone and control it by initiating scans and setting parameters and downloading the data. Or you can just use the device as a standalone device. It has onboard power, so it doesn't require a host. You can take data with preset scan characteristics and store them on a micro SD card for later. You can connect it to your PC or tablet or phone later through Bluetooth or through USB to your PC.
Okay, so it seems like there are a lot of options other than walking around with my spectrometer pointing at things. I'm guessing IoT may be a good place for this technology?
Exactly. You can have real-time material analysis powered by the Internet of Things. So you could send out an army of NIRscan nanos into the field, whether they're measuring crops or measuring hydraulic and industrial fluids or cosmetics or pharmaceuticals, and have high-performance sensors aggregated in a network from your factory or your field applications.
Cool.
Then you can remotely sense and monitor your operations by enabling a centralized machine which can look at different scan results from the field. DLP technology enables high-performance optical sensors on the edge of a network.
Okay, Trevor, I'm really ready to get started now. Oh, where should I go for more information?
If you have any questions, you can go to the TI E2E community. You can learn more about DLP catalog products and other applications at ti.com/DLP. We have a variety of application notes and technical documents that you can look through. You can refer to the TI designs of the NIRscan Nano and other spectroscopy designs to find schematics, layouts, and bills of material. And you can also check out the DLP Design Network, where third parties design their own solutions for you to purchase.
Very cool. Well, I think that's all I have time for today. Thank you so much for joining me, Trevor.
Thank you.
Before we go, don't forget to click that link. There you can find out more information about Texas Instruments' DLP technology. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the on-demand section of eejournal.com or check out YouTube, keyword EE Journal.